Okay, let's ramp things up a little bit with this example. Let's say that the wire in the figure has a uniform linear charge density lambda. What is the electric potential at the center of the circle? So we have a line, half a circle, and a line. So if we look at this, we know that potential is a scalar. We don't have to worry about directions. We can break our wire into three sections. So this is section 1 with a potential V1. This is section 2 with a potential V2. And this is section 3 with a potential V3. If we can find the potential due to each of the three sections, then we can just add them up and we can get the total potential. Okay, sounds like we have a goal here. So our net potential is V1 plus V2 plus V3. First question I'm going to ask for you to think about, do V1 and V3 cancel? So because V1 and V3 are both scalars, they don't have direction, so they can't cancel like an electric field would cancel. The line has a positive charge, therefore the potential here due to this bit is going to be a positive number. The potential here due to this bit is going to be a positive number. They're going to add up. They're not going to cancel. Okay, so V1 and V3 cannot cancel because they're not vectors. They don't have a direction to cancel it with. So where will we start? Let's start with section 3. Let's find V3. I'm going to do a sketch of just portion 3 to start. So in my sketch, I'll put in a coordinate system. I'll put in my wire. Exaggerate the size of it a little bit. Here's my point P. And let's get some distances in here. The distance from here to here, that's just the radius of the circle, so that's r. The distance from here to here is 2r. This is my x-axis, this is my y-axis. And let's see, if I'm going to find my net potential, I know that my V3 is going to be the integral of each little bit of potential dV along that rod. Each little bit of potential is due to each little bit of charge, dQ. So I should show dQ on my picture, and I should show R on my picture. dQ is any little bit of charge along this line. R is my distance between the point where I'm finding the potential and my little bit of charge. So this is my R value. You might notice here that R is measured from the origin to a position on the x-axis. So R is the same thing as x. Okay, let's keep going. What else do we have? dQ, if I wanted to find the size of the amount of charge on this little element of charge, I would do the linear charge density times the length of my little element. The length of my little element is a little bit in the x direction. It's equal to dx. Okay, I think I've got everything here now. So for my integral, I've got k times dq, but dq is lambda times dx. That's divided by r, but r is the same thing as x. I can take my constants out front, so k and lambda come out front, and I'm integrating dx over x, which you probably recognize as a natural log. The limits of my integral, I'm adding up the contributions to the potential from each little bit of charge along the rod. So I have to add up all my contributions along the rod. So my limits of my integral are going to be the limits of the rod from one end to the other. So I'll start right here where x is equal to r, and I'll finish over here where x is equal to 3r. Okay, so the left-hand end of the rod is positioned at x equals r, and the right-hand end of the rod is positioned at x equals 3r. So those are my limits of x. The integral of 1 over x is the natural log of x. It's going to be evaluated at 3r and r. So that gives me k times lambda times the natural log of 3r. Subtract the natural log of r. Here you might wish to use the identity natural log a minus natural log b is the natural log of a over b. True for all logarithms, not just natural log, of course. Gives us k times lambda times natural log of 3r over r. My r's are going to cancel, and I'm left with V3. The potential at this point, due to this section of the rod, is k times lambda times the natural log of 3. Okay, one bit done. The next bit we can do is what about section 1? And remember, we already said that it's not going to cancel. Section 1 is exactly the same as section 3. It's just flipped. So it has the same amount of charge, it's the same distance from the point, it's got the same charge density, same linear dimensions. The electric potential due to section 1 is going to be exactly the same as the potential due to section 3, and that's just due to the symmetry of the system. So let's fill that bit in next. So section 3, or section 1, sorry, V1 equals V3 from the symmetry of the situation. And if you wish to practice your integration skills a little bit, of course you could go through and show that for yourself. So V1 is k times lambda times the natural log of 3. Okay, last step is let's find the potential due to section 2, due to the half arc, and then we're going to sum up all of our potentials and we're going to get our total. So section 2 is next. Let's just do a sketch of what we have. So we have a half a circle of charge. Trying to find the potential right here at this point. So we know that our net potential of section 2 is going to be the sum of each little bit of potential due to each little bit of charge along that distribution, k times dq over r. Let's show our dq and our r on our picture. So dq is a little element of charge along this second part of the wire. There, I've got that shaded in. Hopefully you can see it okay. So that's dq. R is the distance between our point and our charge. And that's going to be equal to the radius of the circle, capital R. Let's see. So we know already that little r is the radius of the circle, capital R. dq is the amount of charge on this little segment that we've identified, our element of charge. dq is the linear charge density times the length. The length is a little bit tricky. A horizontal rod, the length is dx, a little bit in x. A vertical rod, the length is dy, a little bit in y. When we have a circle, the length is a little bit along the arc. So our dq is lambda times our arc length. So ds is a little bit of the arc. Okay, so let's put our values in here now. So we've got the integral of k times lambda times ds over r. One more thing we can do with our s to get our integral is we can ask what is s related to in terms of the geometry of the problem. So if I draw a horizontal line here, I can label this angle theta, and I know that an arc length s is the radius of the circle times the angle. So my little bit of arc length ds is the radius of the circle times the little bit of angle it subtends. And the reason I'd like to do this is because I see that my angle theta varies from 0 to pi as we go around the entire arc. I'm going to fill that bit in next for my ds. Now I see that my r's cancel. I can take my k and my lambda outside because they're constant. Oh, almost off the page there. Integral of d theta. So my dq starts down here, one end of the rod starts down here where theta equals 0. Then as I come all the way around, my theta becomes equal to pi. So I'm integrating from 0 to pi. The integral of d theta, of course, is theta. That's going to be evaluated at pi and 0. So I get k times lambda times pi minus 0. So v2 is k times lambda times pi. Okay, so now what I have is my net potential due to each segment of the rod. I know this one, and this one. To find my total potential, I'm going to add them all up. V equals V1 plus V2 plus V3. V1 was the same as V3, k lambda natural log of 3. V2 is k lambda pi, and V3 is k lambda natural log of 3. Can simplify this a little bit. V is k times lambda outside of 2 times the natural log of 3 plus pi. So there's the potential of that funny wire.